Hello, everyone. We are Darwin, my partners Juan and Walter. This is our project, the quadruped robot for controlled environments. We focus on design and validation. We have four phases. The first, the mechanical design. The second, the math for movement. The third, the controlled. And fourth, the simulation in gazebo to check stability. The robot has a rigid body and four legs. It has 12 degrees of freedom in total. Each leg has three motors, one for roll and two for pitch. The dimensions come from our CAD design. In this case, in our project, we use the inverse kinematic for the legs. We calculate the angles for the motors. We use geometric and trigonometric to find the correct position for the one pit.
Moving on to the control strategy, we implemented body orientation control using roll, pitch, and yaw angles to manipulate the torso while keeping the feet physics. We use a rotation matrix to transform these body commands into specific target position for each foot relative to the body frame. Next. To validate our math, we define specific evaluation metrics in your simulation environment. We check for kinematic consistency to avoid singularities, posture, stability to ensure the center of mass stay within the support polygons, and orientation tracking to measure the error between our commands and the robot's actual state. System architecture. Our system architecture is built on Rust2 and Gazebo Sim. We utilize the quadruped description package for the URDF models and a custom inverse kinematic controller node that computes the joint angle in real time. The environment is a controlled flat plane to minimize external disturbance, allowing us to focus purely on the kinematic validation. Here we see our initial results. On the left, the stance initialization, the robot successfully transitioned from a resting state to a standing heat, stabilizing its posture. On the right, see the body orientation, real-time tracking of body orientation, roll, pitch, yaw, and velocity commands, and robot respond to user input with negligible latency while maintaining stability.
Okay, in this slide, we present the standard control, which is mainly focused on regulating the robot's rolling pitch a voluntary manner. At this stage, the robot doesn't move, but instead adapt its body orientation based on given input sequence. The plots clearly show the dynamic behavior of the system, illustrating how roll and pitch evolve over time until reaching the desired reference. We can observe low overshoot and small settling time, which indicates a stable, well-behaved kinematic control response. The next one. In this slide, we analyze the behavior of roll and pitch while the robot is moving. The main goal is to keep both variables close to zero, ensuring robot stability during locomotion. The plot shows that as the walking speed increases, the system becomes more oscillatory and less stable. Now, this work follows kinematic fair approach where geometry and orientation are validated before introducing dynamic complexity. The tool DOF model provides the stability and orientation control can be achieved purely through kinematic relationship. Additionally, the coupled control architecture separation body level control from leg level inverse kinematics simplify debugging and development in Rust2. Thank you.